Good morning, everyone. So the thing that we're working on at the moment is setting up so that we can build the shell assignment. That's challenge 1. So I want to start off by talking a little bit about strategy for that assignment. Both generic strategy for the challenge assignments and the other hard assignments in this class, and specific strategy for challenge 1, the shell. Now, I want to start off with generic strategy. In this class, we've got programming assignments, and the programming assignments all have about the same grading structure. Half the points are the result of an auto-grading script, and the other half of the points are the result of a manual grader. Now, on the auto-grading script, you gain points by passing tests, and if you pass half the tests, you're likely to get half the points on that part of the assignment. It may be, there are cases where the manual grader, the human grading your assignment may adjust your auto-grader points. If it looks like you're trying to scam the auto-grading script, you may lose points. And if the auto-grading script is too harsh on some assignments, you may gain some extra points. For challenge 1, that's not really what's going to happen. You're likely to get the points that you get as long as you make an honest attempt at the assignment. The other half of the grade is manual grading. And in manual grading, you lose points for making errors. And on the shell assignment, you lose points for not attempting features. So there's a list of features that you're supposed to complete, and if you don't make any attempt at all at those features, you will lose some points. Now, one thing that's important to keep in mind is that it's really hard to predict in advance how long it's going to take to complete an assignment. Some assignments are relatively quick, other assignments are slower, but it's not even that that's a consistent thing for everybody, because in this class, the thing that happens is when you're working on an assignment, you get stuck. As I mentioned at the beginning of the semester, that's the design goal of the assignments, is I'm trying to make it so that you get stuck, so that then you can get unstuck and learn things. But by the nature of getting stuck, everybody's going to get stuck in different places, and people are going to take more or less time to get unstuck. So an assignment that takes one student 8 hours may take another student 12 hours, just because they get stuck in different places and have more trouble figuring out how to make progress. That means that the strategy for working on assignments should take into account the fact that you don't know how long the assignment's going to take to complete, and therefore you want to minimize the potential number of points that you're going to lose if you have to stop early, and you want to maximize the amount of time that you have in case you want to commit more time to the assignment. So you want to start early, but even starting early, you want to make sure that the way you approach the problem is such that you can sort of stop at any point, submit what you have, and then get as many points as you possibly can get for the amount of work you've put in up through that point. The strategy that I recommend is you start on the day you can start the assignment, and then you download the starter code and immediately submit the starter code. Who knows? The starter code may pass some tests. If submitting the starter code passes some tests, then those are points that you just get for free as long as you submit the starter code. Then you should implement enough logic in your version of the assignment code in order to pass the first automated test that the starter code didn't already pass. Just pass the first test. Once you pass that test, go ahead and submit to Inkfish again, and then you've got one more test passed. Those are your points. Those points aren't magically going to disappear as long as you made an honest attempt at passing the autograder script. Just repeat this for each test or each couple of tests if they're clearly so tightly linked that you can do 2 at a time without sort of risking more time on getting distracted by the second test and not finishing the first one. And then at any point you can submit. And for the challenge assignment, the place where I'm expecting you to stop is 80 or 90% of the auto grading tests. I'm not expecting that everybody is going to complete all of the tests. The last couple tests are kind of hard, and they are challenges. You can do them if you want the points, and you should do them if you have the time. But don't feel bad if you can't get the last test to work. The last test is extra hard. Another thing that's important to consider is how to deal with the design of your program. And one thing that is sort of counterintuitive, but I find to be true, is that it's better to start with the simplest possible design that can pass a test than it is to try to go look and figure out what all the tests are and come up with a design that from scratch will solve everything. Even though if you could come up with that design first thing and then implement it perfectly, that would of course be the most efficient thing to do. You know what the plan is, you execute the plan, no detours. You don't actually really understand the whole problem until you try to attack pieces of it. And the other complication is that for something like the shell assignment, there's a bunch of little pieces that you have to deal with whether you're going for like a complex solution or a simple solution. So for example, in the shell assignment, we have the question of should you build an abstract syntax tree, or should you just take the string and try to execute the string in sort of one pass? And the abstract syntax tree is, of course, the solution that you should use if you want to pass all the tests. But you shouldn't start with the abstract syntax tree. Start with a string that all it could ever be is a single word that is a command that you execute with no arguments. Because the work that you need to do to get that to work, to be able to execute a single command with no arguments, or a single command with 2 arguments, because I think that's what the first test is, that work is all going to build pieces of the program, like being able to read a line from the user, being able to differentiate between running in script mode and not running in script mode. This is all stuff that will apply to every version of the program. And getting that sort of infrastructure written and then being able to test it with the like simplest version of the execution logic will allow you to get working code and then make more progress faster. Getting the minimum thing that you can running gives you something to iterate on. Whereas trying to do the whole thing at once, you just have this big mess of code that's never run, and so definitely doesn't work. If you write more than 100 lines of code and don't run it, it's definitely broken, just every time. Yeah, and that's my number one recommendation for writing any software at all. I say never write more than 20 lines of code without running something. If the thing that you run is just printing out an intermediate value of what the first 20 lines of code is supposed to do, so you like read one line of input from the user and then you were supposed to like evaluate it as a shell command, but you hit 20 lines of code, just print out the line of text that you input, run the program, make sure that it works, and that'll help a lot in making sure that you're able to make progress. In the lectures in this class, I do a lot of cases where I'll like write code and it just sort of works on the first try. And that's because beforehand I wrote the code and got it to work. But when I'm typing code in class, I try to execute it frequently, because when I write code, I really do go ahead and write like 3 lines of code and then run it. Write like 3 lines of code, then run it. Write like 5 lines of code, then run it. There are some cases where you can't do that if you're running some complicated data structure, like the linked list examples that I've shown. Yeah, you have to write the code to like allocate a linked list and then do some stuff before you can usefully test it. But as soon as you can test it, you should. All right, so that's my rant on general strategy. Now that I've lost half the class on this video, let's talk about specific strategy. So there's a couple of cases in the shell that are worth differentiating between. We can talk about what the strategy is going to be for each of these in order to evaluate a shell command. And for this, I'm going to assume that you're going to parse your input into an abstract syntax tree and then have a recursive evaluation function. So we've got a base case for our recursive evaluation function. And the base case is that the user is going to input a command. There's M's in command. And some arguments. And what we do here is we're going to fork, because we're executing a new program. So first step is fork. And then the second step is that we're going to execute that command with exec. And then in the parent, we're going to wait on that child. So we fork, run exec to execute the command, and then we wait on the child. And that's our base case. That's the simplest case that we have to deal with. So if we're not in the base case, there's some other cases that we can be in. Here's one case. We've got a semicolon. So we have a shell operator, and that shell operator is semicolon. So to execute this, first we're going to take the stuff on the left, and we're going to evaluate that. And in this particular case, this is just the base case that we talked about. So we fork, then exec that command in the child, then we wait in the parent. But then once we've done this, we're back to trying to evaluate this expression with a semicolon. Then we're going to evaluate the one on the right. So first we do the thing on the left, then we do the thing on the right. In this case, the thing on the right is the base case again. So we're going to fork, we're going to exec that command in the child, and we're going to wait in the parent. All right, so our next case is we have either and or. These are sort of symmetrical. So I'm going to show and. So we have command one. Nope, we're going to do or, because I can't write ampersands. Or. So the idea here is that first we're going to eval the thing on the left. Then if left RV false, we're going to eval the thing on the right. So first we eval the thing on the left, like with semicolon, but we look at the exit code that we got back and determine if that exit code is 0, indicating success, or non-zero, indicating failure. If the command on the left fails, then and only then we recursively evaluate the command on the right. And actually, if we got into like parens, this becomes expression, not command. So we could go the whole way and do a recursive evaluation of a deep abstract syntax tree. So same thing here with and. Again, I apparently can't draw ampersands, but the only difference here is we're going to ask if the command on the left succeeded rather than if it failed. All right, next operation is the background operator. So if we say command one, and then we have an ampersand after it, what we do here is we are going to fork, then in the child, we're going to evaluate that command, and in the parent, we don't wait. So this is kind of like the base case, except instead of waiting, we don't wait. We're going to continue to whatever we're doing next. Now there is a sort of 2-command version of this, or a 2-argument version of this, where we have command 2. And the difference here is that we still don't wait, but now we immediately eval command 2 in the parent process, which probably means forking if this is a base case. All right, next up we have redirect. So in this case, what we're going to do is we're going to, now there's some options here, but the way I recommend doing this is first we fork, then in the parent, we wait, and in the child, we are going to actually do the redirect by, for example, closing. This is going to be standard out, so that's file descriptor number 1. So we'll close 1, we'll open the file for writing, and then after we do that, we eval command 1. And the reason I say we fork first is because now this redirect is only happening in the child process. So when that child process terminates, we don't have to try to restore our state. There's an alternate way we can do this where we avoid the fork and then try to restore the state in the child. And it's possible to get that right, but it's more complicated to think about. So this is the same for redirect in, except we're doing a redirect for file descriptor 0 instead of file descriptor 1. Next case. So we have 1, 2, 3, 4, 5, 6. Yeah, so we just have pipe left. So to do pipe, this is a lot like redirect. So we have command 1, pipe, command 2. This one's the tricky one. It's not that tricky. So first we fork. And again, just like with the redirects, this top level fork exists primarily for isolation. We're creating another process so that when we start to mess with the file descriptor tables and with opening files especially, we don't have to worry about it leaking out into the parent. So we're going to fork, and then in the parent, we're just going to go ahead and wait on that child. In the child, we're going to call the pipe syscall. And the pipe system call is going to give us our 2 file descriptors. Then we're going to fork again. And here, we're splitting into the process that's going to become the left-hand side of the fork and the process that's going to become the right-hand side of the fork. So here in the parent, we're going to, we actually don't know reliably what order this is going to happen in, so I'm going to fork extra times. So we're going to fork, then we're going to wait on that child. In the child, we're going to do, so this is going to be the standard output. So we're going to dupe the pipe to standard output, so we have to close the extra end of the pipe, close standard output, dupe to standard output, and then we're good. And then we're going to eval command 1. Then we're going to fork again here in the parent. So we actually want these things to happen concurrently. So we're not going to wait in either parent until after we've forked twice. We're going to fork twice, and in the parents we'll let it fall through. And then in the child, we're going to dupe pipe to 0. So we're going to replace standard in for command 2. Then we're going to eval command 2. And then back up here in this process, we're going to wait on both children before we exit. This raises the question of what is the return, what is the exit code of a pipeline? If command 1 fails, what does the pipeline return? If command 2 fails, what does the pipeline return? And that is not specified in the assignment. That is difficult to find in documentation. So what you're going to have to do is you're going to have to look at the test to see what's expected. and then you're going to have to try it in bash to see what you actually get. There's a lot of cases where that's true. But yeah, so for every one of these things, you want to think about what is the exit code going to be. But here's pipe, which is our last operator. So that raises one more question. We were talking about what is specified. And another thing that's not clearly specified is order of operations. Someone always asks, what is the order of operations? And the answer is, I don't know, and you're gonna have trouble finding it in the documentation for a POSIX standard shell or bash. So in the cases where you need to know the order of operations, you should formulate experiments and try them in bash, and the behavior that you need for the challenge 1 shell that you're building is just whatever bash does. And you can check the tests to see what the tests are expecting, which will give you the same results. So that is strategy on the shell, and I'll be back in a minute with some more information that you're going to want to know.